Alrighty, today on the Woken Way, it's 9.5 parametric equations. So this is just another way to graph some stuff, and it's particularly used in physics. And again, just like polar, we're going to learn the basics, and then you're going to learn other uses in calculus. But I just want to point out that in our rectangular coordinate system, we have x and y, where x is the horizontal component and y is the vertical component. And then another way we have to measure is r and theta, which was polar, and now we're going to have parametric. And so the first example is not really an example we do, it's just introducing you to the idea of parametric. So let's take a look at it. It says example 1, a ball is thrown from a height of 6 feet initial velocity and 90 feet, and the initial velocity is 90 feet per second at an angle of 40 degrees with the horizontal. After t seconds, the location of the ball can be described by these two equations right here. And what you're noticing is that x and y are not in the same equation like they would be in rectangular. We have two separate equations, one for x, one for y, and we have a third variable now, which is t. So these are called parametric equations right here. And t is called the parameter. So you'll see me throughout these problems circle the t in parameter just because it's a vocabulary word that you're not used to, but I want you to get in the habit of recognizing t as the parameter. Later on over here you can see we have to eliminate the parameter, and that just means get rid of t. So to help you remember that, I'm just circling the t. So we have t as our parameter and we have our parametric equations. Here's that velocity the problem was talking about. Here's the angle, 40 degrees, and t is the time that has gone by in this particular example. And of course, 6 feet is the initial height. It's going to make something like that, right? Because that's the, a parabola is the shape that a thrown ball will take. So that's what's going on here. And these are just introducing you to this. This figure that is graphed when you have a parametric equation is called a plane curve, and it will have arrows on it to show the direction of time. And we'll go over that in a future example. So first, most basic, just like I've always said, we like to have our basics to fall back on. So in polar form, we had to make that table, and it was very tedious. But in this particular unit, some students actually prefer the table. It depends on how comfortable you are with your parent graphs. So let's go ahead and take a look at this. We're asked to graph the plane curve described by the parametric equation. So x equals t squared plus 1 and y equals 3t. And we're going to do this using these steps right here. So step 1 is going to be to select some values of t on the given interval. So I'm going to make a chart here just to organize my information. So I have t, x, y. I have to have those three instead of just an x and y because I had three variables. And then I'm going to pick some t's on the given interval. So here's my given interval right here. It will be different. If you look over at example 5 over here, look at that interval. It's from 0 to pi. It has to do with trig functions being involved. But just pay attention to your interval if one is given. So we're going to pick some values. I'm going to pick my integers. Why am I picking integers? Because they're easy to plug in. And then I'm going to plug them in. So first I'm going to plug into x. This is the equation for x, and then I'm going to plug in for y. So negative 2 squared plus 1 is 5. Negative 1 squared plus 1 is 2. And then we have 1 squared plus 1 is 2, and then 5. And then let's come over here and do this multiplying. We're going to figure out our y's, and we have negative 2 times 3 is negative 6. Then we have negative 3, 0, 3, 6. Okay, so we just made a table. This is our fallback plan. And like I said before, some of you might actually prefer this. You'll be able to decide that in a couple of minutes. You can always fall back on a table. However, if the directions tell you that you need to eliminate the parameter, you need to make sure you complete that step too. Okay, so we're going to plot these points now. Now notice when I plot the points, I'm plotting on a rectangular grid, so I'm not necessarily going to be seeing t in here, but I'll show you what I do to help out. So we're taking care of step 2 right now. We computed that, and actually we're on step 3 where we're going to be graphing. And if you notice, it says connect them with a smooth curve and draw arrows to show direction or orientation along the curve as t increases. So that's super important right there. So what I do to make sure I draw my arrows in the right direction, I'll show you right now. So 5, -6. I'm just going to write t equals -2 right there. Don't have to do it. It's not required, but you'll see why in a second. 2, -3. T equals -1. 1, 0. T equals 0, 2, 3, t equals 1, and 5, 6, t equals 2. So here's my smooth curve. You guys can see what shape is that taking. It's parabolic. Does it always have to be parabolic? No, it's just pretty common. Okay, and then we have to put arrows on this. So this graph actually does stop here and here. They don't always stop, but this one does because you're only asked to graph between -2 and 2 for values of t. And this point right here corresponds, this 0.5, -6 corresponds to t equals -2. So that's why I'm stopping here. Where do the arrows go? I have to be showing signs of increasing t. So if I was going this way, t is decreasing, it's getting smaller, but as I go this way, it's increasing. So I'm going to draw these arrows showing the direction of the curve. So do they have to be right on the points? No, what I say, I just like to put them on the points. I think it looks nice. So up to you. Alrighty, so that is our fallback plan. That's how you make a table. You can make a table, easy peasy. All right, moving on. Okay, what we're going to do now is we're going to do what some people would consider is the shortcut. You get to determine if this is a shortcut for you or not, but what we're going to do is eliminate the parameter. So again, reminding you by circling the t that the parameter is t, so we have to get rid of it, and that's going to produce an equation that's just x and y, and then we're going to use our transformations and things like that to graph. So the way you're going to do this is you are going to solve for t first. So you're going to solve one equation for t. So there's usually an easier choice. There's not a wrong choice, but there's definitely one that's faster. So I'm going to pick the one that's clean. I don't have to square root and remember that plus or minus or anything like that. So I'm going to pick this one. So x equals t minus 2. So then t equals x plus 2. Okay? And then the next step is now that I've solved for t, I'm going to plug it into the other equation. So I'm going to substitute t into other equation. So what that looks like is y equals, I'm going to plug t into here, so that's going to be x plus 2 squared. So if I asked for you to eliminate the parameter, there is the equation with the parameter eliminated. And now I'm going to graph this. What shape does this take? This is a parabola, right? So this is a parabola. And a basic parabola is just x squared. How is this different? Well, it's going to shift horizontally. So I'm going to go left 2. So here's my graph. I'm moving it this way so that I can go left 2. As you recall, a standard parabola has these 4 points. If you don't remember, just make a table for your standard parabola and all of them get moved left 2. Or if you remember the pattern, just do your locator point, which is this guy right here, your vertex, and go from there. So there's the points. I'm supposed to connect these with a smooth curve. There is no interval here, so this graph is continuous, so it's going to keep on going. So a lot of people are like, oh, we put arrows like this. These aren't the same arrows that show orientation. It's okay if you put them on there. It won't be that big of a deal, but we do need to get those arrows of orientation, and the way that we get them is by increasing t. So real quickly, we just need to do a tiny table, okay? So the only reason why we're doing this is to see in which direction we're going to put these arrows. So I like to pick t equals 0 and t equals 1 because they're easy to plug in. So at 0, t is -2. And here y is 0. And at 1, it's going to be -1 and y will be 1. So this point right here, -2, 0, that's t equals 0. And at -1, 1, that's this point, that's t equals 1. So it's getting bigger as it goes up the curve. So my arrows are going to be like this. If you want to throw a couple more in there, you can. Alrighty? So now we're going to move on to the next one, which says sketch the plane curve represented by these. It's the same kind of problem. Of course, it's slightly different. Why is it slightly different? So that you're able to expand on your knowledge base. We don't want to keep giving you the same ones. So eliminate the parameter t. So how are we going to do this? Okay, so first thing we got to do is solve for t. So which one do I want to solve for t in this case? You could pick this one, but then you got to multiply everything by 2, or you can pick this one. It's up to you. I'm going to pick the x equals the square root of t. So then I get t equals x squared because I have to square both sides. Alrighty, and then the next thing I have to do is substitute t into the other equation. So what that looks like is here's y equals 1/2 t plus 1. Well, we have already said t is going to be x squared, so we get y equals 1/2 t squared plus 1. I just wrote t squared. This should be 1/2 x squared plus 1. There we go, that makes sense. So again, when you're asked to eliminate the parameter, there's the equation. This is now a rectangular equation in x and y, and we have to graph it. And guess what? This one's a parabola too. The 1/2 in front is going to be a vertical compression. You don't really have to know that, but what you do need to know is that we take all the y values and multiply them by 1/2. Another way of saying that is we cut them in half. And then we also have this one right here, which is making the graph then go up 1. So you always take care of compressions first, then reflections, then horizontal and vertical. So let's go ahead and take a look at the graph of this right here. So this one totally just drew a funky graph. I was drawing the same one as that one. Oh well, we'll make it work. It's not going to be a big deal. It's just going to be scaled funny. So let's go ahead and graph this. So the parent graph is these 4 points right here. And then this tells me to cut those in half. So I'm using the same pen. I can keep my eye on it, so it's okay. If you can't, use a different color. Or I'll make bigger dots so you can see where the dots are. When you cut 0 and a half, it stays 0. So there's my 4 points for the 1/2, and then I have to move everything up 1. Okay, so here is my curve right here, and right now I'm not making the full curve. And the reason why I'm not making the full curve is you have to be very, very careful with these. I'm going to write my little note right here for you. So note, okay? The domain of our rectangular equation, which is this guy right here, must match the domain of our parametric equations. So look at this. If we have x equals the square root of t on this, what's the domain of this? What are my inputs right here? It has to, because it's a square root, it has to be greater than 0 or equal to 0. So the domain here is from 0 to infinity. The domain of this right here is all real numbers, but this has to match this domain right here. So I'm going to write that right there real quick. Domain is from negative infinity to infinity. That's because we have no square roots or zeros in the denominator. So where do we graph from? Well, our graph is going to be from right here. It's only going to be this piece right here. Why is it only going to be that piece? It's only going to be that piece because of this restricted domain right here from 0 to infinity. So again, how do we figure out our arrows? We have to do our tiny table, t, x, y. Again, just picking 0 and 1. Square root of 0 is 0. 1/2 times 0 plus 1 is 0. And then when I do 1, I get 1. And then this one, I'm going to get 1 1/2, or 3/2 if you prefer. So right here, oh, that was funny. This shouldn't be 0. This should be 1 right there, right? Because you do 1/2 times 0, 0 plus 1. So this one is t equals 0. And then this point right here is t equals 1. So my direction is going up, not down. So it should be like that. This little piece is a little tricky for students. Just keep this in mind. These domains have to match. There's like a red flag that goes off when it's a square root because the domain of a square root can only go from 0 to infinity, which means when I plug in 0 to infinity here, all my x's can only be bigger, 0 or bigger. This right here, I could plug in negative x's. It would give me this piece of the parabola, but since my domain of my parametric equation is only from 0 to infinity, I don't graph that, okay? So that one's a little tricky. This one is also a little tricky. So I'm going to put a tricky on this as well. Tricky, tricky. For sure you're going to want to study this. I'm going to give you an extra mini example on that one too. So you're like, what the heck? There's cosine and sine involved. So I'm going to give you some steps for when cosine and sine are involved. We still are kind of we have to eliminate the parameter t, but we don't solve one equation for t and then plug it into the other, because how do you solve this? You would have to use an inverse cosine or an inverse sine, and we don't want to get into that. But there is something super cool about this, and you will love it. I just know. And if you don't love it, you will at least appreciate the beauty that comes in this problem right here, because it's one of my favorite problems altogether. So we have to eliminate the parameter and we have to graph it. So here's what we're going to do first. I'm going to copy these equations real quick, and then I am going to isolate sine and I'm going to isolate cosine. So let's start with cosine. So how do I isolate cosine? I'm going to divide both sides by 5. And over here, divide both sides by 2. Okay, so step 1, isolate sine t and cosine t. Okay, moving on. Step 2, you are going to square both sides. So I'm going to take x over 5 and square it. And I'm going to take cosine and square it. Cosine t, I should say. Same thing here. So I get x squared over 5 equals cosine squared t. And then I get y squared over 4 equals sine squared t. So the next step was to square both equations. And now here comes like the super fantabulous, awesome math right now, okay? Here's what we're going to do. We're going to take the left side of this equation. By the way, that should be 25. And we're going to take the left side of this equation and add them together. Why, you ask? Well, now I'm going to take the right side of this equation and add it to the right side of that equation. Mathematically, that makes sense. It's super weird, but it should make sense. If I add the two left sides, it should be equal to the same thing as adding the two right sides. Okay? Why do I want to do this? What did you learn in chapter 5? What does this equal right here? This equals 1. And now you're going to be like, wow, are we really going to pull from Math 3 or Algebra 2? Yep, we're going to pull from that class right now. What shape does this make? That right there, if you can recall, makes an ellipse. Crazy, huh? So how do we graph ellipses? So we are going to, whatever's under, let's start with our center. So the center of our ellipse is whatever numbers are here. Since we don't have any numbers there, it's going to be 0, 0. So here's my center. And whatever's underneath the x, if I take the square root of that, that's how much I stretch in the x direction. So these equations are squared, but the graph is not. And what I mean by that is this is squared 25, but when I go to graph it, I'm going to go 5 in each direction. Again, why am I going in the x direction first? Because that's what's under the x. And then under the y, the square root of 4 is 2. Now, this is the ellipse. And in this particular problem, though, we were given an interval. We're only graphing from 0 to pi. Here's 0, here's pi. So I'm only graphing that top piece right there as my final answer because this doesn't tell me to graph all the way to 2 pi. It's just from 0 to pi. Also, this was our equation finally with t gone. T was still in here, now it's not. Okay, so we need to do arrows, and you got to be a little bit fancy with your tiny table in this case. So here's my t, x, y. I'm not going to pick 0 and 1 for this because I actually need to pick angles because my input into trigonometric functions are angles. So I'm going to pick 0 and pi over 2. And here's my little shindig. Here's 0. That's the point 1, 0. And at pi over 2, which is up here, it's 0, 1. Okay. When I plug in 0 into this first parametric equation, the cosine of 0 is 1, and then I have to multiply it by 5, so I get 5. And then when I plug in 0 into the second equation, sine of 0 is actually going to be 0, and 2 times 0 is 0. Then I'm going to do the same thing for pi over 2. The cosine of pi over 2, which is, so where's my graph right here? This point right here is 0. 0 times 5 is 0. Sine of pi over 2 is 1. 2 times 1 is 2. So here was t equals 0. Here's t equals pi over 2. So my directions are that way. Alrighty. Now, on your test, you, or in your work even, you might have a problem that looks like this, that says x equals 1 plus cosine t. Let's make it 5 cosine t. And then maybe y equals negative 3 plus 2 sine t. And students get stuck. They're like, what do I do? Same thing first. Isolate sine t and cosine t. So instead of just dividing first, I have to subtract the 1 and I have to add the 3. So it looks like this. X minus 1 equals 5 cosine t. And then I would divide out the 5. So then I would get x minus 1 over 5 equals cosine t. And when I square that, I get x minus 1 squared all over 25 equals cosine squared t. So that was just this one. And then I would do the same thing for the other one, and I would end up getting y plus 3 squared over 4 equals sine squared t. And then I would continue with using that Pythagorean identity. And then my center here would be 1, negative 3. Okay, 1, negative 3 from that right there. And then I would go 5 in the x direction from my center, not from the origin, and 2 in the y direction. So that one you might see on your test, so make sure you study this. Alrighty, we are moving on. Flip it over. Now we're going to work backwards. So we are going to be given the rectangular equation, and we'll need to come up with a set of parametric equations. Here's the thing. This is going to be the easiest thing right here. When you're working backwards, you're going to let x equals t. It just makes your life so much easier. This one is on the test as well, and students forget to study this, and it's super, super easy. You literally let x equals t sub into the other equation, and you're done. So I don't want you to miss those easy points. So again, we're working backwards. On the front side, over here, we were taking two parametric and going to one rectangular. On this side, we are going from one rectangular to two parametric. So how do you do that? The easiest thing to do is to let x equal t. Okay? If x is equal to t, there's my first equation, my first parametric, and my second one, all I'm going to do is plug that t in for x. That's it. Those are my two parametric equations. Maybe you're going to try and get fancy. I don't know. It's up to you. But maybe you're like, you know what? I'm going to let x equal t plus 1. Does that work? Yes, it does. We would get y equals negative. And you're going to want to put this one in parentheses, plus 9. Or maybe you're going to be like, oh, I'm going to let x equal t minus 5. Or 5t or whatever, and you're just going to be careful and make sure you plug in appropriately. All of these are acceptable answers for this question right here. All right, but this one's by far the easiest. This should be your default. This is going to make your life easier if you just let x equal t. Okay, why? Well, that's this last part down here on this type of problem. You cannot let x equal anything. So your x must equal a function that allows x to take on all the values in the domain of the given rectangular equation. Okay, so let's take a look at this right here. I want you to consider if we let x equal t squared, right? So if we let x equal t squared, let's take a look at the domain. If t equals negative 1, what do we get? X equals negative 1 squared plus 1, sorry, not negative plus 1. I don't know what's going on. Which equals 1. There. Okay? So again, I'm just walking you into something, so if you're like, what the heck is she talking about? It's okay. I'm trying to explain why you can't let t equal or let x equal anything, all right? I'm not really going to give you these tricky ones on the test, but you will have a basic one, so make sure you study these types of problems. Okay, back to this one. So if I let t equal negative 1, and then when I plug in negative 1 here, I'm going to come out with an x. We need to keep in mind that this domain, which you can see right here, is all real numbers. It's from negative infinity to infinity, right? So my outputs for x need to be from negative infinity to infinity. But when I'm plugging in negative values of t, or positive values like positive 2, what's happening? Am I ever going to get a negative out of this? No. Because that square is taking all my negatives and making it positive. So what that leads us to conclude is that if x equals t squared, then all of our x's are going to be greater than 0, but the domain of our rectangular equation, which is y equals negative x squared plus 9, is all real numbers, or negative infinity to infinity. So they don't match, and they need to. So you can't just let x equal anything. Alrighty, last piece of stuff is probably the easiest one. First, take a look at these equations. These are examples of parametric equations for circles, ellipses, hyperbolas, and lines. You do not have to memorize these. If it's on your test, they'll be given to you. What you do need to know is that these right here are in your textbook, but they're in the homework portion. So whatever homework problems that have been assigned, look right above them, maybe a couple lines up above, and these will be there. Okay, so you don't have to get your notes back out to do these. These are in the textbook, embedded, I don't know, embedded. Not an English teacher, embedded in the homework problems. Okay, I'm just telling you that in case you can't find them, because you're going to get to it and it's going to give you a question like this right here that says, find a set of parametric equations for the circle. And you're going to be like, I have no idea how to do that. She didn't show us how to do it. Just look up above. It's super, super easy. Okay, so parametric equations for a circle are x equals h plus r cosine t and y equals k plus r sine t. Remember, with a circle standard form, h is the x-coordinate of your center and k is the y-coordinate. Alrighty, at this point, it's just plug and chug. You're trying to come up, here's our rectangular information, and these are our equations for parametric. H is 4 plus r is 6. Ta-da, plug and chug. Over here, 6 plus 9 sine t. There's your two parametric equations. That's all you have to do. Okay, next, an ellipse. Are you going to use those two same parent parametric equations? No, because that was for a circle. So let's take it and we'll look at what it says for an ellipse. It says x equals h plus a cosine t. And what else do we get? Y equals k plus b sine t. And you're like, what is this a and what is this b? HK is obviously going to be the center, HK. A and b are how much you stretch in that direction. So a is the horizontal stretch, and b is going to be the vertical stretch because it's with the y. So if you need help, when in doubt, graph it out. So look at this problem. It says, I'm just going to graph it over here real quick. The center is 4, -1. That's here. The vertices are 5 units above and below center. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And the endpoints of the minor axis, that's just, if this is the vertices, those are the major axis. The co-vertices are on the minor axis. So it's 3 units to the left and right. Okay, so here's my ellipse. So how much did I stretch? You got to be careful here. This is the vertical stretch of 5, and this is the horizontal stretch of 3 right here. Okay, so let's fill these out. X equals 4 plus horizontal stretch. Even though the 5 is written first, you don't put it first. We're talking about horizontal and vertical components. And y equals k, -1 plus 5 sine t. All right, plug and chug. Last one is the line passing through 3, 1, and 9, 12. How do you do those? Well, look down below at your equations. X equals x sub 1 plus t times x sub 1, x sub 2 minus x sub 1. And y equals y1 plus t times y2 minus y1. All right, let's call this one point 1. So that's x1, y1, and this is point 2, x2, y2. So we just plug and chug. We get 3 plus t times 9 minus 3, and we get y equals 1 plus t times 12 minus 1. And then we get x equals 3 plus 6t, and y equals 1 plus 11t. Super duper easy. Again, we don't really get the application of all this fun stuff. It's called pre-calculus because it's prior to calculus where you get to learn all that fun application stuff. But it's a new skill we're acquiring, and at least we get to learn the basics. And that is it for today, you guys. Have a great rest of your day.